Okay, guys, this is the second half of the notes on section 5.4 for concave up and concave down. We did this last example, example 2, and basically what you do is you take the second derivative, you set it equal to 0 to get your critical values. Just don't forget to do the domain errors to get any critical values. So here we got no critical values, here we got 2 from the domain errors. I always draw those little squiggly marks in there to make sure that you don't label them as actual points of inflection if they are domain errors. So find your test point, figure out whether it's positive, negative. Positive means it's caving up, negative means it's caving down. Points of inflection down here, the definition of point of inflection is a place where it changes from concave up to concave down as long as it's not a domain error. So here we did not have any points of inflection because even though it changes, we had domain errors there. So that's what this next example is going to be on the next page. Point of inflection here because it's going from up to down. Point of inflection here, it's going from down to up. Point of inflection here, it's going from concave up to concave down. Okay, even though along both of these functions it's increasing all the way through, increasing, well, I guess it's starting to decrease down here and decreasing here. So when it's changing, increasing, decreasing, it's not really related to concave up, concave down. Okay, this one's increasing from negative infinity to infinity. Concave up, concave down are not associated with increasing, decreasing, so be careful of that. All right, points of inflection. The point C, f of C, is a point of inflection if either f double prime of C equals 0 or it does not exist, which means that basically these are the domain errors. Domain errors or the second derivative is equal to 0. So those are the two ways that you get points of inflection. All right. This next example, I gave you the graph. You won't be given the graph on the homework, but just so you can relate it back, you can see. Determine the points of inflection and discuss the concavity of the graph. All right, so I didn't go ahead and give you the second derivative, but it's easy to find. Let's do just f prime. Do f prime, it's 4x to the third power minus 12x squared. Okay, then f double prime is 12x squared minus 24x. Okay, now it's the second derivative that you want to set equal to 0. Okay, and then what I would do from there is I would pull like a 12x out and left with x minus 2, I think. Yeah. So setting both equal to 0, 12x equals 0, and x minus 2 equals 0. You'd divide by 12, and x would be 0, and you'd add the 2 over, and x would be 2. So you've got two critical points, or two critical numbers. Okay, now domain errors, you always want to look at those, but since this does not have any denominator or any square roots in it, you will not have any domain errors, so there are none here, but always make sure you check that. Okay, so I have two critical numbers, that means I have 3 test intervals. Okay, the first critical number that's going to come up is 0, so I'm going to do from negative infinity to 0 as my first interval, from 0 to 2, and then from 2 to infinity. Okay, now I don't have to put squiggly marks on either one of these because I don't have any domain errors. All right, test value, I'm going to do like negative 1, 1, and 3 here. Okay, this is a typo right there. That should be f double prime again. I copy pasted that table over and I forgot to change it. So should still be the second derivative. You're going to plug these numbers into the second derivative. Okay, so 12x squared minus 24x is what you're plugging these numbers into. Okay, so plugging negative 1 in first. Okay, this is going to be a positive 12 plus 24, so that's a positive number. Okay, so the conclusion, that's going to be concave up. Okay, if I plug in a positive 1 in here, positive 1, this is going to be 12 minus 24, so that's concave, or that's going to be a minus, and concave down. Okay, and if I plug 3 in, 12 times 3 squared minus 24 times 3. This is 12 times 9, which is 118. No, that's not right. 108. 108. Minus 24 times 3 is 2172. So still a positive number. Concave up. Okay. So I have my concave up, concave down, concave up. Since none of those are domain errors, I'm going to have a POI here and I'm going to have a POI here. So at 0 and at 2 are going to be both points of inflection. I'll write that over here. POI is going to be at 0 comma something and at 2 comma something, okay? To get those y coordinates where those are located, you plug it into the original function. So if I plug 0 in here, 0 to the 4th minus 4 times 0 to the 3rd power, it's still going to be 0. So I have a POI at 0. Okay, you can see that from the graph. 2, if I plug 2 in, 2 to the 4th power is 16 minus 4 times 2 to the 3rd power. This is 4 times 8. So 16 minus 32 is negative 16, I think. That's probably about right, negative 16. Okay, so those are POIs because they change concavity at those points and they are not the squiggly domain errors. Okay, all right, now this altogether is very different. The second derivative test, okay? You'll see that as problems in your homework. The second derivative test is different than what you're doing up here, okay? So second derivative test has to do with maxes and mins, okay? So in the previous section, section 5.4 or 5.3 and 5.3, we would do the first derivative. Let's write this over here. We would do first derivative, derivative, set it equal to 0 to get your critical numbers, and then plug in, you would do a test point, and then you would find increasing, decreasing, and then you would get maxes and mins. Okay, judging from where it was increasing, where it was decreasing. Okay, now you are finding maximums and minimums by using the second derivative test. This is a different way, a different method other than this. Okay, sometimes this is easy, sometimes you'll find it easier to do this procedure, to actually do the increasing, decreasing stuff, okay? But maxes and mins you can find using the second derivative, okay? And here's how this works, okay? Find the relative extremis, so you're going to take this and you're going to do the first derivative, okay? So this would be negative 15x to the 4th plus 15x squared, okay? You're going to set that equal to 0 to find your critical numbers, just like you did in the previous section, okay? So I'm going to pull out negative 15x squared, and I get left over x squared minus 1 equals 0, okay? So if I set negative 15x squared equal to 0, I get x equals 0. If you set x squared minus 1 equal to 0, you will get x equals plus and minus 1. Because you add the 1 over and take the square root, and you'll get plus and minus 1. Okay, now, in the previous section, you take the derivative, set it equal to 0, and then you create test intervals. Okay, since I have 3 critical numbers, I would have 4 test intervals. Okay, but you're not going to do this procedure again. You are going to now, with these points, take the second derivative. Okay, you're going to take the second derivative, and my numbers that I'm going to use are going to be x equals negative 1, x equals 0, and x equals positive 1. Okay, I'm going to take the second derivative, and I'm going to use those things. I'm not going to have test intervals anymore. Okay, you're going to have actual, like, coordinates. I'll put coordinate points. Okay, so take the second derivative of this function right here. Okay. F double prime is going to be negative 60x to the 3rd power minus 30x, I think. Yep. Okay, now, you're not going to have a test value anymore, so we're going to completely skip this step right here, but you're going to go ahead and plug these numbers, the critical numbers from your first derivative, into your second derivative. Okay, so negative 1, I'm going to plug it in here, negative 60 times negative 1 to the 3rd minus 30 times negative 1. Okay, this is going to give me positive 60 plus 30, which is going to be a positive number. Okay, I'm going to plug 0 in. 0 to the 3rd power times all that times 0 is going to be, that shouldn't come out as 0. Yeah, it does. Okay, so I'll put 0 here. I'll put 0 here so it doesn't look like negative. Okay, and then you plug 1 in. So positive 1, positive 1, all right? Negative 60 times 1 to the 3rd power is negative 60 minus 30. That's going to be a negative number, okay? So now you do your interpretation. We took our critical numbers from our first derivative. I'll put like notes down here. Critical number from first derivative. D-E-R-I-V, I cannot spell, into second derivative. Okay, you take those critical numbers, you plug those into the second derivative. You don't do your test intervals anymore. You just take these numbers, plug them into the second derivative, and you get numbers here. Now, this is the backwards thing. If your number, or whatever you got when you plugged it in, if this number is greater than 0, which means it's a positive, you have a minimum, okay, which is the opposite of what you would think. I would think greater than 0, I would have a maximum. It's the opposite way, okay? If you have a negative number, then it's going to be a maximum value. Okay, it's the opposite of what you think, all right? So what I have going on here is there is going to be a minimum value at -1 comma something. There's going to be a maximum value, because it's negative right here, at +1 comma something, okay? And then since this came out to be 0, that means that this is neither. This is actually a POI. If you see from the graph, you can see that it is neither a maximum or a minimum at 0. Okay, I have a minimum at -1, I have a maximum at +1, but I have neither at 0. Because when I plug that into the second derivative, I get 0. Okay, so to figure out the maxes and mins, the y-coordinate, you're just going to plug that into the original equation. If you plug it into the original, I'm totally going to cheat. -1 is -2, +1 is at +2. So I have a max at 1 comma 2, and I have a min at -1, -2, okay? So this procedure is called the second derivative test, because you take your critical numbers from the first derivative and just plug them straight into the second derivative. If it's positive, it's a min. If it's negative, it's a max. If it's 0, it's neither. It's probably going to be a POI. That is as opposed to taking your first derivative, setting it equal to 0, finding some test intervals, putting a test point, finding increasing, decreasing, then finding where your maxes and mins are located according to increasing, decreasing, okay? Sometimes this procedure is a lot faster. Now, if your second derivative is really, really ugly, this one was nice because it was just a straight polynomial function. But if their second derivative involves like the quotient rule or something really nasty, it might be easier to do this procedure. But this one was a straight, easy polynomial function. Second derivative was a lot easier to do, and then just to plug in, and then you can get your answer. Okay, so second derivative test is used to find maxes and mins. It's not the same thing as finding concavity up here. Okay, so that is all I have for you. If I went too fast on that video, go ahead and nope, there's nothing on the back. Rewind it. Hold on. I don't know if you guys are in the library right now or where you're at, but this is homework from this section, if you didn't get it written down already. So there is that. Yeah, there you go.